So thanks for coming today. I'm Dr. Rob Sowby. I'm a civil engineer. Any other civil engineers in here? Probably not. Good. That means I can say what I want. I've worked for Hansen, Allen, and Luce. We're a local consulting firm headquartered in South Jordan. I've been there for 6 years, focusing on water resources studies, drinking water infrastructure, crossing over into energy management. So I kind of find myself at this interesting intersection of water system engineering and industrial energy efficiency. Water facilities are industrial sites. They have industrial electric rates. They have the same kind of lights and HVAC and pumping systems that a lot of other industrial sites do. But it's very different in a lot of ways, and you'll see some of those as we go along. But in particularly as it concerns your assessment coming up here at the university or at West Jordan on November 6th, water systems are more risk averse than some of the customers you usually deal with, because if they fail in their job, it becomes a public health crisis. And so if you encounter some resistance to implement some of your recommendations, it's totally normal, okay? So don't take it personally. It takes a little bit of messaging and finesse to get through to the water system operators and their engineers and staff. But it's great that you've been invited to do that. That means they're open-minded, they're thinking about energy efficiency already, and so we already have the hardest part over with. So today we're going to talk specifically about water facilities as they concern pumping. We'll talk about pump curves, we'll talk about power computations, horsepower, VFDs. This is a lot to cram into a short session, so bear with me and do your best to keep up. So first, there are a lot of different kinds of pumps, and I'll show several photos here, but a common type is a centrifugal pump. You can see the anatomy here. It has a suction side, it has a discharge side, and a lot of mechanics in between. But at its most basic, a pump is a device that turns electrical energy into a combination of head and flow, or pressure and flow. And these are the components that make that happen. Water goes in the suction side, it's spun through the impeller, through the volute, and the area of the cross-sectional area of the volute increases as it exits, so it maintains constant velocity through the pipe chamber, and then onto the discharge side, or here labeled the pressure side. There are other types as well. For example, these ones that are vertical turbine pumps that are exactly what they sound like. They're a vertical configuration, and these bits at the bottom are called bowls, and you can stack up as many bowls as you need, usually 1, 2, maybe 5 or 6, sometimes more, depending on the head you need. So you stack these up, you add head, and then it takes in water from the bottom, adds head as it goes up through these various bowls, and then discharges out the top side. The motor, of course, on top with the line shaft that drives the impellers. So a lot of pumps that you'll see, especially the bigger ones, are going to be these vertical turbine pumps, line shaft driven with the big motor sitting on top. Sometimes they have more than one motor because water systems have to have some redundancy. They either have to have a backup generator and or multiple pumps so they can service one and still run the other, and so forth.
Rob, real
Yeah.
quick, just because our group is super new, can you, in that picture, point out the motors?
Yeah, so the motors are these two parts on the top. You can see the power coils coming in from the ceiling. We'll see several more photos here. Let me back up a little bit. So again, there's 3 or 4 motors on the top. They're usually these kind of R2-D2 looking things. You have that shape with the rounded top and the cylindrical body. And then they drive into the line shaft that spins the impellers. And so in this case, water is coming up through pipes in the ground, up through the turbines here, or the impellers and the bowls. It's driven by the motor and then discharged to this side. And this assembly here is a control valve. Some other monitoring equipment. So again, a lot of what you'll see will be these vertical turbine pumps with the line shaft driven motors. Smaller pumps will be like the first one we saw, where it's horizontal, it's inline, centrifugal pump. More vertical turbines here. And then this one is a centrifugal pump. You can see it here in the foreground. Water's coming in from below, spinning through here, coming this way, spinning through here, and then out the top. So pumps come in all different shapes and sizes and brands and colors and manufacturers. But they all have the same thing in common, which again is that they convert electricity into a combination of pressure and flow. Okay, so let's go through some basic definitions. So let's consider the case where we're lifting water between two water tanks. In a public water system, this might be between pressure zones. There could be some other configuration within a particular water treatment plant, for example. So we want to lift the water from bottom to top. So one thing we need to know is the suction head. That's the height of the water above the pump. And I put that on here because it really doesn't matter where the pump sits within a certain range. You can't suck it too high or you'd have too much head on it. But it matters what the water level is. So the difference in water levels is what we're looking at, and that's what we call the static head. The difference between the water level in the lower tank versus the water level in the upper tank, regardless of where the pump sits. And again, we just put the suction head on there because the pump has to have some minimum amount of suction head in order to function. Is that complete though? What else are we missing? Yeah, what happens when you move the water? Is there other head we need to add?
Yeah, the pressure drops across your pipe.
Yes, so it's friction, head loss, right? And it's invisible, so it's kind of hard to show on this graph, but it occurs in the pipes and in the fittings and things. As fluid rubs against the pipe wall, there's some friction there, and it slows the water down, loses some pressure. And so we have to make sure that we consider that too in our head calculations. And so the total dynamic head, the TDH, is what we're really looking for, is the static head plus the head loss. So if the water is just sitting there in the tanks, that's just static. But as soon as you start moving water, you have to overcome the friction, right? And so you have to add a little bit more. So the total dynamic head is the head that the pump feels when it's running. Okay, not when it's stopped, not when the water's at rest, but when the fluid is moving, when the pump is running, what does the pump feel? That's the question you need to answer, and that's what we call the TDH, total dynamic head. I know this is all technical, and we'll bring it all together with some practice in a bit. So a few definitions we need to know before we can introduce the pump equation are capacity. We call that Q, flow rate. In this case, throughout this presentation, we're talking about water. It's incompressible, standard pressure and density, temperature. So it's a lot easier to work with than like compressed air and other things where you have to consider ideal gases and compressibility. Hydraulic efficiency. You don't ever get in 100% of what you don't get out 100% of what you put in, right? Basic thermodynamics. There's always some loss due to friction wherever it is along the chain. You plug it in, goes through the motor, through the pump, into the fluid, blah, 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 until you get to the end. And you multiply all those efficiencies going along. And so this hydraulic efficiency is the ratio of the pump output to what we call the brake horsepower, which is the input. And it's a fraction or a percentage, a fraction between 0 and 1. Total dynamic head we've already defined, the head the pump feels when running, including losses, and in the case of groundwater, drawdown. So I'll mention this briefly. With a well drilled vertically for groundwater, when the water's at rest, that's one thing. As soon as you start to run the pump, what happens? The water starts to suck down. We call it a cone of depression, right? And it's not a psychological term. It's a hydraulic term. And so that's called the drawdown, is the difference between the natural free water surface and it is when it's pumping. So you have to consider that in the case of wells. Speed in revolutions per minute, we won't deal a whole lot with that, but it is important. And then diameter, the size of the pump impeller. And I'll explain later on why that's important, but suffice it for now to say that for a given size of pump casing, you can get different sizes, different diameters of impellers. And that's one thing manufacturers do to save money. So for a particular pump casing, you can get a 7-inch up to a maybe 10.5-inch impeller or whatever it is, and they have different performance characteristics.
Can you review what impeller is?
Yeah, so the impeller is It's like a propeller, except it's a similar concept. It's the device that actually imparts power to the fluid. Okay, it's a blade, it's a propeller kind of thing. In pumps, we call it an impeller. Okay, so with that background, we are prepared to learn the pump equation, which many of you may know. So you guys should memorize this, whether it's for water systems or for air or other things. So this one, I should note, is particular to water and certain units of measure, okay? So this tells us, and we can derive this from basic thermodynamics, but we've simplified it here. So P is the brake horsepower, or bhp, and that is a function of the flow rate times the total dynamic head, again using gallons per minute and feet for these units, divided by 3960 times the efficiency. Does anybody know what this Greek letter is called? It's my favorite Greek letter. Eta. Very good. So I've given the similar presentation like a dozen times to different water operators and engineers, and nobody knows what it is, even if I offer prizes and things. So I'm glad I didn't offer anything this time. So yeah, that's eta, ETA, and it's kind of a long-legged N, and that represents the efficiency we're talking about. 3960 here represents what?
Conversion.
Yes, first of all, unit conversions, because this is not empirical. Oh, this is empirical. We're using gallons per minute and feet as our units. What else is in there besides unit conversions?
Gravity.
Sorry?
Gravity.
Gravity, yes, you're getting there. It's fluid properties. Density, right? So this is specific to water. If we were pumping a different fluid, it would have a different denominator. Okay? So with that in mind, you being the efficiency engineers, what in this equation can we alter to decrease the power draw?
Flow in the head.
Okay, so you can decrease the flow.
So
You can
pressure drop.
you can decrease the head. Yeah, the pressure, the head, same thing.
Increase the efficiency.
And you can increase the efficiency. Right? So you want to make a small numerator and a big denominator that brings the whole quantity down. Good. And then if we're talking about energy, we can also add hours to reduce the runtime. Yes?
When you have efficiency percent of 0 to 100,
Here it's a decimal, 0 to 1. Is there another question here?
Yeah, what's the difference between brake horsepower and any other horsepower?
So the brake horsepower is what you have to put into the motor. Okay, so the pump takes some energy and then the motor has some efficiency too. So the brake horsepower is what you actually put in.
So that'd be like what you see on your bill as opposed to what you're actually getting out of the pump.
Right.
Okay.
It's what you get charged for, if you want to think about it that way. Yeah. Okay, so we will revisit this equation several times, and we've got some calculations to practice, so be ready to do that. Any questions about the definitions of the equation? Pretty straightforward, right? It's a function of head, flow, and efficiency.
And your power unit is?
Here is horsepower. Okay. And as we'll learn in just a moment, in fact right here, 1 horsepower is 0.75 kilowatts. So you can go between them pretty easily. And that's all I wanted to show on this slide is that the brake horsepower is what you put into the pump, and then the motor power is that divided by the motor efficiency, something like 94.5% for high efficiency motors these days. And then the motor power in kilowatts is the motor power in horsepower times 0.75. So you can do that conversion pretty easily. So now knowing power, and you guys, this is great. I'm used to talking to water operators who don't really know anything about energy management except the demand charge. They know about that because if they push the button, they get charged $10,000. So they know about the demand charge. But they have a hard time differentiating kilowatts and kilowatt hours and efficiency and these other things. So I feel like I have home court advantage with this group. Do you have a question?
Actually, can you go back one
Yeah.
slide? Just a cliffhanger for next week.
Ooh,
We're gonna take a look at that factor, how to get the motor power from various field measurements and information. That's a calculation that I've seen the team regularly be off on, so we're gonna take this one more step next
Okay,
week.
very good. Good preview of coming attractions. Thank you, Julie. So once we have power, we can easily get to cost. And you guys are really good at doing this, so I don't have to spend a lot of time on it. But kilowatts times hours gives you kilowatt hours. Kilowatt hours times cents per kilowatt hour gives you a cost, however many hours are run during the year. Okay, so now we go on to pump curves. How many of you have seen a pump curve before? Okay, almost everybody. How many of you have designed a pump using a pump curve? Okay, a couple. This is very good. So again, this is one of those things that water operators are not familiar with. Engineers get pretty good at it, but it shouldn't surprise you that a lot of people who are not familiar with pump curves think that it's a conspiracy just to keep engineers employed because they're so mystifying to read. Okay, there's like all these curves and little dashes and who knows how many axes there are. 1, 2, at least 3 axes on this graph. So we're going to learn how to read a pump curve. And those of you who have already done so can help me do it. Oh, I wasn't supposed to disclose that calculation. That was supposed to be animated. But let's just ignore that for now. We have a pump with an 11-inch impeller. It's pumping water and is operating at 500 GPM. What are the other operating conditions? So let's do this together. Okay, so just to orient you, on any pump curve, the horizontal axis is always the flow rate. There might be different units, but it's always the flow rate. So here we're going to look at the top one, which is gallons per minute. There's also units of cubic meters per hour, which we're not going to use. On the vertical axis is head, in feet in this case. On the other axis is head in meters, and then these curved lines, these kind of U or C-shaped lines, are zones of hydraulic efficiency. And there are particular points on this curve where the pump will run, depending on the impeller size. So here we have a 14-inch impeller, 13, 12, 11, 10-inch impeller. So like I mentioned, for a given size of pump casing, you can look up the pump curve from the manufacturer, and they can help you do this. You can find a lot of these online these days. You find your impeller size, so we're given 11-inch impeller, and then you read the other parameters. So I like to start with the flow rate. So we're given 500 GPM, so that puts us about here, and I'm going to read up. So when in doubt, read vertical, up or down on the graph. Read up until I get to the 11-inch impeller, which is right there. And it's pumping. So then at this point, we need to figure out what the other conditions are. So let me step through this. So there we are. What is the operating head? Yeah. It's 100 feet. So we have 500 GPM, we have 100 feet of head, and reading in between the efficiency curves, where do you think that lines up? I know my vertical arrow is a little bit shifted, but...
Is it like 52? I can't really see that.
Yeah, so we're looking about right here. It's somewhere between 54 and 58. So we'll call it 57, okay? Yeah.
Just some quick question on so you have static head and you have head loss.
Yes.
Right? So I'm just kind of curious, I'm curious to see, or I'm kind of confused on, if you have a pump that is designed for, let's say, I don't know, 11 feet of head, for example, or 100 feet of head. So is it pumped to overcome that amount of pressure losses?
Yes.
Or is it usually above spec, or is it usually just at that?
It's meant for that. So you design to the total dynamic head. Maybe you put some safety factor in there because you're not going to get it exactly right.
Okay.
You might need an 11 and 13/16 inch impeller to do that.
Well, okay, so then back to that example where you have 2 tanks.
Mm-hmm.
Are the 2 tanks at different pressures then? Or?
So 2 tanks are at different elevations, and the water's not pressurized. It's just floating in there.
Okay.
It's just breathing. And so we're trying to move water from one tank to another.
So in that example, it's just to overcome the head loss.
Yeah, first of all, the static head, the elevation difference, plus any head losses that occur during conveyance.
Okay.
Yes. And we'll have some practice doing this in just a few minutes. Okay, so with the calculation is shown here. I won't make you do it. But this is our pump equation. Q times H divided by 3960 times the efficiency. And that comes out to about 22 horsepower. And incidentally, on this graph, these diagonal lines happen to be horsepower. And so we could verify that our point here lies just between 20 and 25, which is what we'd expect based on our calculation. Okay? So we'll do this a few more times, but any questions up to this point? Again, pump curves can be mystifying, and that's okay. Yeah.
Can you explain the difference between hydraulic efficiency and motor efficiency?
Yeah, so hydraulic efficiency is what the pump does. Motor efficiency, beyond that, is what the actual electrical piece of the system does. So pump efficiencies, without knowing anything different, I would say 70% hydraulic efficiency. And without knowing anything different, I would say 95% motor efficiency. You multiply those two together, you get your overall efficiency. We call that wire-to-water efficiency, where you go from the motor through the motor, through the pump, to the fluid. Okay, so there's our pump curve. And we read the efficiency there, and we compute our values. Okay.
Question.
Yeah.
Is there a range for like a good and bad efficiency?
Yes.
The pump efficiency, you mean?
Yeah. Usually you won't see anything over like 83%. It's hard to get any more efficient than that. And really, anything below what it's designed for might be considered unacceptable. But there's always going to be some difference. So I won't give it a lower limit. That's up to you as the efficiency engineer to determine. Yeah, James?
Have you ever seen savings opportunities from switching out of replacing a low efficiency pump with a higher efficiency?
Yes, absolutely.
Are those economical?
It depends, right? That's always a scientific answer. I'm not trying to be ambiguous, but it does. Is it a big pump? Is it a small pump? Are they running it 10 hours a month? Are they running it 500 hours a month? It just depends on how long they use it and what the payback would be.
And again, just to clarify, there's one conversation about the pump efficiency, and there's another conversation about the motor efficiency.
Right. We're talking primarily about
We're talking
pumps here.
today.
Yeah, but we recognize motors are part of that too. Okay, so here's a different kind of pump curve, and this time I won't reveal the answer. But the only difference here, so we still have our flow, our head. The only difference here is that this is the efficiency curve. So it's either these U-shaped zones or it's an arc, okay? And this little notch, by the way, this represents that's the design point that some engineer specified for a particular project. So we'll ignore that for now. And again, a range of impellers that cover this range of flow conditions. I should mention here that relative to my point at the beginning, where I said that pumps are devices that turn electricity into a combination of flow and head, this graph, a pump curve, shows what that trade-off is between flow and head. So here you have low flow but high head. So you can pump a little water a long way if you're on this part of the curve, okay? And if you're down here, it's just the opposite. You can pump a lot of water a little ways when you're down here. High flow, low head. And then this curve defines everything in between. So that's why you don't see anything up in this part of the curve, because you can't get high head and high flow for the same amount of power. Okay, does that make sense? Now, it's not to say that you can run your pump anywhere in that range. There's a particular sweet spot you want to be at, and where might that be? At the peak efficiency, at the top of that arc, right? It's like riding a bicycle or a manual transmission car. You can tell when you're when it's like you're pushing a little too hard or you're pedaling too fast and you want to find the right gear, the right speed to match the effort you're putting in for the speed you're going, right? And so that's what a pump curve is. You don't want it to be too little or too much, but right in the middle where it's best efficiency. Okay, so let's do this once more. We have a pump with a 7 3/8 inch impeller operating at 320 GPM. What are the other operating conditions? So I want a volunteer to come up and walk us through this pump curve for these points. I'll give you a minute to think about it. It's like we did the other one. We start with the flow and we read up and find the head. (320 gallons per minute). 7 3/8 inch impeller. So that's what we're given. We need to figure out the rest and the energy implications. See, I only know a few people's names in here, so I can call on them. Eric or James? Chris? One of you want to volunteer? No? Okay.
You said your name first.
Yeah,
I
that's
guess.
true. Yeah,
You can do it, Eric.
Yeah, come on up.
But Chris is
So I'm understanding it right. This would be your 3.75 or 7.375 inch impeller.
Yes.
So you'll find then 320 gallons per minute. down
Okay.
here. And
Good.
you're
And we follow
operating-
that up till it intersects the
There.
impeller
So
size.
your efficiency will be about 62, 63
Okay.
probably. And I was trying to figure out how you figure out the power from that.
Okay. Let's do the head
But
first.
your head would be right there as well, so about
So-
100 feet.
Okay. And then the efficiency, so if we were, where were we, 320, if we were here, how do we know not to go, well, do we go this way to the efficiency? Do we go this way or do we go up? How does that work?
Isn't this efficiency on the
That
side?
is efficiency on the side.
So you would just do it right where it's at that horizontal level, right?
So you read, when in doubt, you read up.
Read up.
Yeah, so here was our point, and then this is the efficiency that corresponds to that flow rate. Okay?
So what is this efficiency on the side?
So, so that's, yeah, and then we read over here to 70. Instead of reading from our point here, which would have been 60-something, so that's where it can be a little bit confusing, some nuances of the pump curve. Okay, let's give Eric a hand. Okay, yes?
So efficiency is only a function of flow rate?
No, it's a function of the pump.
But, so, yeah, but right here, the only thing that's changing your efficiency is your flow rate.
Yes. If we were to look at a different kind of pump, it would have a different efficiency curve.
Okay,
Yeah. So on this particular curve, yeah, it's a function of the flow rate.
not impeller size.
And no. Well, let's think about that. So let me back up to this other one. It'll be a little bit easier to see. So does impeller size affect the efficiency? So here we have large impellers, small impellers. And here's 50%, and we're working toward 65%. Does impeller size matter when it comes to efficiency? Yes. How?
As the impeller gets smaller, the efficiency decreases.
As the impeller gets smaller, the efficiency decreases. Does anybody know why that is the case? Yeah, because you have a smaller blade in a bigger casing, so there's a bigger gap between the impeller edge and the pump wall, the casing. And so there's sloshing going on in the pump, right? But if you have a tighter fit, a bigger impeller in the same size casing, it's more efficient. So just case in point, so with a 10-inch impeller, the best you can do is like 54, maybe 53% efficiency on this particular curve. But if you have a 14-inch impeller, then you can get 65 or higher. Okay? Yes?
Why would they not make the casing smaller for the 10-inch?
They,
Use the bigger impeller.
because
Why would you ever use the smaller impeller?
why would you ever use a smaller impeller? Because it will give you the flow rate that you want, right? So here, if we were using the 10-inch impeller at the best efficiency point, that would only give us 400 gallons per minute, right? And so we want the bigger one over here. Or it could be that, we want this pump casing because it's the cheapest, and so we're going to put in the small impeller and get that corresponding flow rate. Yeah?
All of this is gonna be assuming that we don't have a VFD.
Yes, that's right. So this is fixed speed pump. We'll get to VFDs later on. Yes?
But in the other curve, it's not dependent on the impeller size, right?
Sorry?
In the other curve, the one in the next slide.
Yeah, so this one, it's a little bit harder to see without the zones, but yeah, it matters too. Because, if we're given the best efficiency here, is going to be different depending on the impeller size.
Does your efficiency depend on the head as well, or no, in this curve?
No, so it's a function of the flow rate. That's how these curves are set up. It's all a function of flow rate. You choose your flow rate and then you read the other values.
So I'm sorry, how are you reading the efficiency on this curve again?
Yeah, so this one we were at 320 and at this impeller size, 7.375, and we read up to the efficiency curve, not left, not right. We go up and then read that value over here.
So if you are reading up, then the efficiency is not dependent on the impeller size, because whatever the impeller size is, you're gonna go up with the efficiency.
But you'd have a different flow rate.
So like if you had a flow rate of 480, you couldn't use that smaller impeller size.
Right. So here, it's off the curve, right?
Or if you were lower at like 300 or 200, could you even have a larger impeller size at 200, or would it have to be that lowest impeller size?
Yeah, so that's why I went back to the other graph, because it's easier to see the effective efficiency or the effective impeller size on efficiency. Okay, so let's move on. So these were our design points. And Eric showed us we had 1,250, so we said 1,300, 1,250 is close. We read up to the efficiency curve and got 70%. And so now with that, go ahead and compute, using the equation, the horsepower. And I do have some handouts that I'll circulate here. So one of these, we'll use this sheet later on as a worksheet. This one has the equation and some space to do some math. I think we should have enough here. So you know those points from the curve. Go ahead and compute the horsepower. This is not a test. It's an exercise.
You know why? It's war shorts with these on.
That is correct. And we could also read that here on the curve, right? So we could calculate it, but that's what this line actually is. We could also read it here just to confirm. So 320, again, read up and then over to come to about 145 on the horsepower. Okay? Good. Any questions about how we got those values? Yeah, in the back.
Have you ever run into issues in practice with the bottom curve that we need to worry about in this class?
The net positive suction head, we won't worry about it here. So in one of my early slides, I showed that you have to have a certain amount of water above the pump in order for it to function. That's what the net positive suction head is. Yeah?
So on this curve, using a different impeller size would give you a different head without changing the efficiency or the power or the flow rate? If you were to change the impeller size, you would get a larger or smaller head, but it wouldn't affect how much your power or your efficiency?
So that it's hard to tell. That's why I like to use the other kind of curves where it shows that trade-off a little bit better. But yes, so let's consider if we had a different impeller size, say this one, 320 here, it would have the same kind of efficiency. This is a duplicate slide. Okay, so
Question.
yeah.
Do we round those numbers up? Because I got 144.3. It was 145. Do we round?
Yeah, you can round up. Can you buy a pump with 144.3 horsepower?
Of course, no.
No. So you probably go to 150, right? Okay. Okay, just a couple more slides, then we'll take a break. So some important definitions. We talked about static head already, the difference between the two water levels when it's at rest. And so that's one extreme of being 100% static head, no water moving, just difference between two water levels, okay? The other extreme is 100% friction head, where we don't change the elevation and it all goes to pressure, okay? Now, that's important because you're going to have a combination of both in any given water system. It probably won't be strictly static and it won't be strictly friction. It'll be some of both. There will be some minimum amount of static head you have to overcome, and then the friction head will go up as the flow rate increases. And that's what we call a system curve. It's the opposite of a pump curve. And we'll put these two together after the break. The system curve is what the pump feels, what the pump experiences. So this one, let's start with this one. This is a static head only, so it doesn't change. That's why we call it static. And then this blue one is friction only, so that at zero flow, there's zero friction, but as the flow increases, so does the friction head. And then typically, it'll be some combination of the two, where there's a minimum amount we have to lift between the tanks, 100 feet, for example, and then we have to add even more head as the flow goes up. And this will become apparent pretty soon. So that's just to say the pump curve is one tool. Combined with a system curve, we can put the two together and figure out what the best pumping scheme is for the hydraulic conditions. Okay? Any questions? I know we'll come back to to system curves in a few minutes, but I want to make sure that we're all caught up on those things so far.
So the static plus the friction is not just the summation of the other two?
So we're not adding these curves, they're just examples of three different kinds. Yeah. Okay, let's take a 5-minute break. Great, so now it's your turn to be a pump designer, okay? So you got a blank grid as part of your sheets there. So this is your
Enough sheets, by the way?
There are extras too.
okay.
Can you pass the extras back up?
So this is your assignment. You get to design a new pump station. This pump is going to be set at elevation 4820. The discharge point is 4860. First question, what is the static head? (4820 to 4860). What's the static head? 40 feet. Okay, that's the minimum amount of head we can expect. Okay, just the elevation difference. It's not going to get any less than that unless there's an earthquake or something. Okay, so we have static head of 40 feet. So on your curve, you're going to first draw the system curve. Or let's see. Yes, the system curve. So is the system curve going to look like this or like this?
That's gonna curve up.
Yeah, so the pump curve goes this way, system curve goes this way, goes up to the right. Okay, so at zero flow, what is your system head?
40.
40. Okay, so mark that on your graph. Use a circle, and we'll put in some other points momentarily. Okay, so at zero flow, we have 40 feet of head. Okay, now, according to the following information, you have to add this head loss according to the flow rate. So 100 GPM, you have 1 foot of friction head. So then what's your second point going to be? 41. Okay, do you get where we're going here? So draw your second point at 41. And then at 200 GPM, we have 40 plus 5. Okay, so finish that out and complete your curve all the way through 500 GPM. Okay, I'm going to circulate here and make sure it's going well. Yep, and then connect the dots if you haven't already. Okay, has everybody got a system curve? Should look something like this. If yours looks different, talk to your neighbor. Okay? So what does this represent? It's the response that we expect from the water system depending on the flow rate. So if we're pumping 500 GPM, we expect 90 feet of head, of which 50 feet is friction and 40 feet is static, right? Okay. So this tells us that if we want to design a pump for a certain flow rate, we know how much head to expect. We can usually develop these kinds of system curves from a hydraulic model. It's a computer simulation of the water system. It's kind of like Google Maps for water distribution. It knows the connectivity and the speed limits and all the different things. And we use that to produce this system curve. Okay, so you're part of a design team. So put your initials at the bottom of the page and pass your paper to the right. You're going to pass it up the chain to the next engineer. And they're going to make sure that your system curve looks like theirs.
Sorry, I wasn't very good. I'm not great at drawing straight lines.
Okay, now, did anybody get a system curve that looks different than the one they just passed? Okay, good. That means we're consistent. Okay, we're a good team. Okay, now you are going to select a pump. Okay, and it has these properties. So here's your pump curve. Before you draw, which way is the shape going to go, up or down? So as you go from left to right, it's going to go down, right? That's the trade-off, head to flow. So go ahead and mark these points with an X and connect the X's. Before I forget. I'm noticing that these lines are a little more carefully drawn than the first batch, now that you know you're passing your work to somebody else. The quality improved. Isn't that interesting? Okay, has everybody got a pump curve? Okay. Okay, so now you should have something that looks like this. So what's interesting about these curves? They cross. What does that mean?
That's where it's going to run.
Okay, so you caught yourself. You were going to say it's the optimal point. It may or may not be the optimal point. We'll come to that later. But that's where the pump will run, where the pump characteristics match the hydraulic characteristics. The system curve intersects the pump curve, right? That's where the pump will operate. Okay, so almost there, if I hadn't reformatted my slides. Okay, so do you remember from the first slide in this exercise, what was our design flow rate? 350, okay? And so how did we do? Are we close to 350? We're a little bit more, right? So we're actually more like 400 GPM here, okay? Or sorry, I know my star's off. Okay, 375, I think it's 370 now that I think about it. Okay, and we read that head to be what? What's the head there? 65, okay? Okay, so we know the pump should run at 370 GPM and 65 feet. So what are we missing in order to compute the horsepower?
Efficiency.
Right, we need an efficiency curve. So initial your work, pass your paper to the right. And then we'll construct the following efficiency curve. Okay, again, question, does this one go up or down? Yes, it goes up and then down. Who said that? Brooke, Courtney? Yeah, good.
Yes.
Okay, a few more seconds. Okay, can we move on? Everybody got their efficiency curve? So isn't this cool? You got one curve that goes up, one curve that goes down, and one that does both. Okay? You need to know which one's which. Okay, so to your point, is this the optimal spot for the pump to run?
No,
Why not?
because it's on the downside.
Right, so the optimal spot would be here somewhere around 300, but we're a little farther to the right. So what's our efficiency here? Let's see what the slide says. 54. Okay, let's use 54%. Depends on how accurately you drew your squiggles. Okay, so now you have everything you know, everything you need to know to compute the horsepower. So go ahead and do that. And I'll put this slide up just to refresh your memory. We know the flow, we know the total dynamic head, and we know the efficiency. Okay, who's got an answer? How many horsepower are we talking here? 11.2. Okay. So next question, is it a big pump or a small pump? Small for water system, okay. So how many kilowatts are we talking then?
9.
8.4 kilowatts, okay? So we got our horsepower. We had 370 times 65 over 3960 times 0.54 gives us 11.2 horsepower. Then we multiply that by 0.75 and get 8.4 kilowatts, all right? Now, how much will it cost to run, assuming it goes 24/7 over a year? And remembering that we also have to consider 94% motor efficiency. So 8.4 divided by 0.94 gives us 8.9 kilowatts that's going into the motor, okay? So we start with 8.9 kilowatts, run it all year at 6 cents per kilowatt hour. How much does that cost?
$4,678.
Okay, we have a second witness for that value. We may be rounding a little bit. Okay, so first of all, how many hours in a year? This is a good number to keep in your head if you don't have it already. 8760, okay? So that gives us 78,000 kilowatt hours times 6 cents gives us, we'll call it 4680. I know there's a little bit of rounding there, that's fine. Okay, initial your paper and pass it once more. This may be the last. Okay, now let's say it's 1 year down the road, this thing's been operating, and you take some measurements, and you find that it's actually pumping 450 GPM instead of 370 as designed, and instead of 350 as we originally intended. So let's recompute what that means. So use the curve you have and figure out the new operating conditions at the new flow rate.
Same head?
No, your head will have to change.
Good question. So start with the flow rate. That's given. You take some measurements and you say, whoa, it's going at 450 instead of 370 or 350. Okay, what do we got this time? How many feet? 50 feet, okay. And what kind of efficiency? We read down and then over. 40%, yep. Okay, the pump should run where we expected, but it's not. We got some new things here. And so go ahead and compute, well, it's shown here, 14 horsepower times 0.75. Now we have 10.6 kilowatts. What did we have before? 8.9. So we're getting more flow, but we're also using more power, right? Because we have 40% efficiency instead of 54. That's the big difference.
Wait, but if you install an 11 horsepower motor, how could you suddenly find it to be outputting 14 horsepower?
Maybe you put in a 15 horsepower motor, because they don't come in 11.4 horsepower increments. Okay, good question though. So you always oversize your pump and motor a little bit. That's just good practice. But as we'll see, it can be a little too much sometimes.
It's a great question because it's funny, but yet that is the reality of the real world. So the sooner you learn these sort of standardizations, the more quickly you'll adapt to the real world.
Mm-hmm. Remember one of my first consulting jobs, I was assigned to compute a pipe size for this or that, and I came up with, I don't know, like 12.6 inches. That's the pipe diameter we need. Well, they don't come in that size. They come in 12 and 14, and depending on the material, you get inside and outside diameter. Anyway, So like, oh, yeah, okay, 14-inch pipe then.
You can save yourself a little bit of an embarrassment. And
Yeah.
you can show the value of the IAC in real world experience.
That's right. No, this is a great question, though. Okay, so just looking ahead here. Okay. So let me back up here. So if we're not operating at the point we originally intended, and also not operating at the point we expected, where our curves intersect, what went wrong? Is it a problem with the system curve? Is it a problem with the pump curve? Both?
Be the system curve. Well, the pump curve's constant. We could have got the wrong pump.
Okay. But you're right. So is it more likely that the pump curve information was wrong, or that your characterization of the system head was wrong?
Our characterization.
Right. So whose initials are on the first curve? That's who computed the system curve. So that's the person you fire because they didn't do it right. Maybe not fire. That's probably a little strong, but critique may be the best word. So that person came up with the system curve, but what we found is that it's too conservative, right? So we expected it to be there, 370 and 65, and that's where it crossed our pump curve. But in reality, the system curve looks more like this. It's a lot shallower. Okay, there's not as much friction head as we thought. So remember, this part is the static head, and then anything beyond that is the friction head. So this one's actually pretty flat. That explains why with the same pump curve, we're getting different response in the performance, because we're over there closer to 450 instead of at 370 where we thought we were before. So this happens all the time, that that we're too conservative in the system curve, and those changes propagate throughout the design until you get something that's way bigger than it needs to be. Yeah, James.
Out of curiosity, is there how is head measured? If there's a simple answer, great. If not, so.
Yeah, so I mean, when we do this in our firm, we use a hydraulic simulation to figure the head. Sometimes we make field measurements, but it's pretty well known at that point, and we calibrate that in the model. And so we do a few runs at different flow rates and kind of plot these points, and that's what we design to. Okay, so let's suppose that we want to get it back to our design point of 370. What do we do?
Install the VFD.
Okay, that's one option, VFD.
Valve, the throttle.
Okay. Trim the blades. Very good. So excellent. So let's talk about those in reverse order. So trimming the impeller, what does that do? Right, so you remember we're putting a little slosh in the pump mechanism by making a bigger gap between the blade and the wall. And so that brings the flow rate down a little bit, okay? So you mean you have to pull the pump, send it to the manufacturer, resize it, the impellers. That's a good option.
Will the impellers get shorter with time? Do they wear down?
They wear out, absolutely. Especially when you're talking about like raw water and wastewater that has got stuff in it, grit and particles, sand. They wear down over time. Yeah, drinking water, yeah, they wear down, but it's fairly clean water, so it takes longer. But yes, you do have to be aware of that. So then, what was the first one you mentioned? Throttling. Okay, and what does that do?
Increases the static or
The friction head. Yeah. Okay, so that's what you can do here. So if we want to move it back, then we crank the valve and we create 20 feet of friction head to force the curve back up here to our design point, okay? And that's probably an okay short-term solution. Why is that bad for in terms of energy efficiency?
You're still using the same power.
Right. And you're putting in power, and then you're taking out power by adding friction, right? It's like shining a lamp on a solar panel, right? You're putting energy in, and then you're just taking energy out. It doesn't make sense. Okay, so then by doing that, just by turning the valve, we bring it back to the design point. Okay. We could also equip it with a VFD. That essentially shrinks the pump curve toward the origin, right? So for a certain pump speed, you just essentially copy the curve. There's a little bit of geometry involved, but in affinity laws and so forth. But you shrink the pump curve toward the lower left. And so if that's the case, then we bring it back. Instead of adding a bunch of friction with the throttling valve, we just slow down the pump to whatever speed, say 83% here, and that accomplishes the same purpose without adding any friction head. We're just regulating the flow, okay? And so now we are back to 370 GPM to our design efficiency, but it's a lot less head, right? So this graph just shows, different valve positions and speeds and so on. Essentially, how you can get multiple pump curves out of a single pump by having a variable frequency drive. But we have to remember that if we were to keep it running at 450, we're also creating more water over the same amount of time, right? If you run 350 GPM all year, that's one thing. If you run 450 GPM all year, you get more water. And so we have to normalize it in a different way. So that's what these last couple slides are. And you can see how much the cost difference is. So we had 8.9 kilowatts as designed. We figured 4680 per year. Installed, it cost a lot more because we were having such low efficiency. Efficiency is not shown here, but with 50 feet, we had a lot lower efficiency. And then when it's throttled, it's exactly the same as it was when we designed it. We're bringing it back up to that point by adding friction. But with the VFD, we can take advantage of the fact that we overestimated the system curve, and we can cut out that friction head. And then we bring it back to our design point, to our much lower head, because it's the shallower curve, and a lot lower cost. But again, we're pumping more water, so we have to normalize by the volume, and that's what's shown here. Again, designed and throttled are the same, 400 kilowatt hours per million gallons. It's a good metric to use, by the way, when you're doing this stuff, kilowatt hours per million gallons. Throttling, installed, it's a little bit better because you're getting more flow out of it at lower head, but adding the VFD is the best, brings it down to 288. And so that's a 28% difference in the energy intensity from the VFD. Is it cost effective? Again, the scientific answer is it depends on a lot of things, and that may be part of one of your analyses, one of your assessments going forward. Okay, so that's the end of the pump curve presentation. We have a few minutes for questions, but otherwise, thanks for letting me come. I appreciated the chance to talk to you guys. Again, home court advantage for me when it comes to energy efficiency and pump calculations, energy calculations. That's great. Any questions? Okay, let's go green shirt here.
How do you go about getting those alternate pump curves for the VFD?
Yeah, so it's you can get those from the manufacturer. What pump curve corresponds to certain VFD speeds, and it'll often show up on the pump curve. Yeah. Do you have a question?
Yeah. So would it be a similar outcome if we were to trim the blades?
It would be. It would be like, yeah. So you wouldn't be adding any friction. Well, maybe a little bit because you're sloshing in there, but you're just controlling the flow rate essentially. So that's a good option too. And maybe that costs less than a VFD. VFD gives you a little more operational control to respond to varying flow conditions.
Yeah.
So it's just a good practice anyway. But if that's too cost prohibitive, trimming the impellers maybe just as well.
And how do you go about estimating the costs of that?
That's your job.
Well, so is it a service that's usually done through the manufacturer, or is it a third party?
Trimming the
service?
impellers, it's a manufacturer service.
Okay.
Yeah.
So in all honesty, Rob, or not honesty, but just a level set, this group's strengths are calculations. our current strength is not costing. So
Mm.
given that,
Ah, okay.
what would be the top 3 things, points of advice you would give
For
for
cost
costing?
estimating. Yeah, it's not really my forte either. When it comes to pumps and equipment, I contact the manufacturers and get quotes, and they're happy to do that. Especially if you say it's a student project, you know, they'll be, oh yeah, that's cool, they'll help you out.
Are there particular manufacturers that you work with? These guys hit walls with manufacturers
Yeah.
that don't want to give you costing, so are there manufacturers you would recommend?
Yeah, so there's Nickerson pumps.
So spell it.
I don't know, NIC, ERSON, I don't know,
Okay.
maybe it's NICK, Nickerson Pumps
That's
is
not a
one.
familiar, I asked,
No.
but that's not a familiar brand.
Yeah, and there's what's another one, Western Pumps and Service, I think,
Is that Utah
yeah.
specific? Okay. Jesse and Ari and Landon, you guys getting this? Other questions, just in general about the content, before I totally use this opportunity to ask a timely question?
Do those same companies also offer like VFD curves?
They may, I don't know,
Okay.
yeah.
Do you use ASHRAE curves, like VFD curves and stuff regularly?
No,
They're
not
more on-
personally,
They're more on the air side.
yeah, yeah.
How often do you see pumps that are like in parallel or pumps that are in series compared to like one single pump that can just do the job by itself?
In water systems, there's usually more than one pump, but that's just for redundancy. Especially in smaller water systems, they'll only run one pump at a time. The only time you'll see several pumps running together is if it's like a water treatment plant or something that's trying to match some kind of flow rate. Essentially, if you have enough pumps of different sizes, it's almost like having a VFD. You can respond to any demand condition, right? But to your question, yeah, a lot of them, we don't see pumps in series. You see them in parallel. If they need to turn on a second one and get a little bit more flow, they do. Yeah, so as you probably know, so with pumps in series, you add a head to the same flow. With pumps in parallel, you add flow to the same head. But two pumps, so one pump running at 1,000 GPM in parallel with another one doesn't give you 2,000, does it? Because there's more friction involved, because that curve goes up. So if you have two 1,000 GPM pumps that each produce 1,000 GPM by themselves, you put them both together, you might only get like 1,500 or 1,700 GPM. You might not even get that much, depending on the ability of the downstream distribution system to accept that kind of flow with minimal head loss.
So would you recommend getting many different sized pumps or a VFD usually to
Uh,
manage demand?
Yeah, so again, probably VFD would be it depends, but
Right.
yeah, VFD is usually what I see. Having multiple pumps takes a lot of space and a lot of cost. But if you really have a big range, sometimes the VFD can't go a range of, like a factor of 4 or 5 on the flow rate, but multiple pumps can. Good questions. Okay, thank you everybody.